trade-offs between recall and precision. Before ending today's video, make sure to subscribe button down below and like the video for more content just like this. All right, so to begin with, we discussed recall and precision in the previous tutorial. We discussed how precision basically explains that, basically relates rather, how if the value of the values that are predicted as being true, how many of them are actually true, right? And it gives a percentage there for the number of values that are predicted as true relative to the total number, or not the total number of values, but whether or not those values are true. Recall related the values that were true, the model predicted as being true, to the total number of values that were actually true. And so those are the two things with regards to recall and precision. What the harmonic mean allows us to do is it allows us to combine precision and recall into a single measure called f sub 1. So what allows us to do is it allows us to compare these two values, these two percentages, and particularly it gives emphasis to the smaller values. And it creates a harmonic mean that is skewed towards the lower value. And so the equation for harmonic mean here is 2 divided by 1 over the precision plus 1 over the recall. And what this allows us to do is it allows us to find a mean between these two values while skewing the harmonic mean more closer to the value that is smaller. Now, the value that is smaller would be the value that has a lower precision or a lower recall. If it has a lower precision, that means of the values the model predicted as being true, many of them were actually not true. If the value had a very low recall, that means that of all the actual true values, there were very few that the model correctly predicted as being true values. Okay, so if either of these values goes down, then it's going to shift the harmonic mean, or f sub 1, to a very low number. And so you see here that you can see here how this relationship works. You see here that let's say we have a precision and a recall of 0.9. Well, that's going to give you a harmonic mean of 0.9. Now, let's say I move one of those values extremely down. Let's say I move position from not position, but precision rather, from 0.9 all the way down to 0.1. So I skewed this particular value, down all the way to 0.1. You can see how it affected the harmonic mean extensively just because I skewed one individual data instance all the way down. But if I took the mean of these two individual values, let's say 0.9 plus 0.1 divided by 2, I would get 0.5. Yet harmonic mean, in particular, the way that it's different from a regular mean, it shifts it down more towards, skews it more towards the direction of the either precision or recall that is more lower. Okay, so that's the difference. That's what harmonic mean is really good at. So by doing this, we'll be able to identify whether or not we have one trade-off as being too much skewed towards one side. All right, so too much skewed towards the smaller direction. All right, so let's go ahead and talk about how we can implement this in scikit-learn. So in scikit-learn, we can go to the metrics module and import precision score and recall score. And so we can calculate both the precision score and the recall score. So you can see precision score is 0.837 and recall score is 0.1651. And then from there, we can import f1 underscore score from the metrics module and calculate that harmonic mean. Now, when we calculate the harmonic mean, it is going to recalculate both the precision as well as the recall score, and we get an F1 score of 0.732. Again, that 0.733, which is much lower than the 0.95 that we were able to get through cross-validation scoring. All right, so now that we've seen these two things in play, we want to analyze what exactly are the trade-offs between these two. Is it possible to have a situation where both the harmonic mean and, not the recall and the precision are both extremely high values? Well, it is actually not possible because there are trade-offs between each of these, and we're going to discuss why these trade-offs specifically occur. So we're going to go into a little bit more about how the SGD classifier works. The SGD classifier is a binary classifier in that it predicts whether or not a particular training data has the characteristics of a particular target value, or if it does not. It's basically binary in its nature. Now, keep in mind, in our case, we're predicting if the value is 5 or it is not 5. The SGD classifier does not necessarily have to predict whether the value, what the specific value is. It doesn't have to predict what the specific value is. All it has to do is it has to say, is it a value that is not 5 or is it a value that is 5? It doesn't have to predict the exact value if the value is not 5. So keep that in mind there for how it works. All right, let's take a look here at trade-offs. So this is basically how the what the SGD classifier does behind the scenes. So you see here that we have thresholds. So we see here that we have 3 thresholds. Just take a look at the middle threshold. For each individual training data, or not training data, but the attributes that come in. In our case, we have 784 pixel values that are coming in as input for our model. Okay, for that individual input, what the model is able to do is it is able to determine a decision score. We have to understand that everything that we're working with our SGD classifier is probabilistic in nature, meaning we cannot say with a 100% certainty that a given number of inputs will reach a target value of 5. We do not know, have 100% certainty. Everything is on a range. And if the value is more likely to be 5, then we will assign it as being 5. If it is not very likely, then we will not assign it as being 5. Everything is probabilistic in nature. And so, because of that, in order to determine whether a number is 5 or it's not 5, the SGD classifier basically assigns a decision score to each of the individual rows. Okay, so for each input that is coming in, each row, attributes that are coming in, it assigns a decision score. And then, based on whether that decision score is above or below a particular threshold, we will determine whether or not the model will determine whether or not it is 5 or it is not 5. Or in this case, it is true or not true, not true being false. So, in this case, let's say the decision score was above the threshold. If it is above the threshold, and again, we're just looking at the middle threshold here. Don't forget about these 2 thresholds on the left and the right. But we're just taking a look at the middle threshold. If the decision score is above the threshold, then that means that the number is true. That means it's going to be 5. Okay? If it is below the decision threshold, then it is not 5 or it is false. Okay, so if it's above the decision threshold, then it's 5, then it is true. If it's below, then it's false. Very simple, right? Now, let's go ahead and say that we moved the threshold over to the right. Okay, we move the threshold over to the right. Well, what is the decision score in essence? The decision score is basically saying how likely it is that a particular number is mapped to a particular target value. It says whether or not this number is equal to 5. If the decision score is higher, right? Let's say the decision score goes from 70% to 90%. It is more likely that the number is 5. Okay? It is more likely that the number is 5. And if the decision score goes up, if the threshold goes up, then it's more difficult for you to get a decision score that is above that threshold, right? If the decision score is lower, it is very easy to get many data values that will fall above that particular threshold. If the threshold is very high, it is very difficult to get decision scores that will go above that threshold. It's very difficult. Most of them will fall below that threshold. Okay, so you can kind of see already there's some trade-offs that we have to make. So let's say we shift the threshold over to the right. And what's that going to end up happening? Well, what's going to end up happening is that in order for a value to come to the right of this threshold, okay, now we're looking just at the right threshold here. In order for a value to come above the threshold, the decision score has to be extremely high. If the decision score is extremely high, is it more likely or less likely, okay, that the number is going to be 5? Yes, it is going to be more likely that the number is 5 because we have a greater probability of it being greater than 5. And if the decision score is very high, if the threshold is very high, then the decision scores that fall above that threshold have a very high chance of being 5. And so when we shift the threshold to the right, we have a greater chance of all the values that are now going to fall above that threshold as being equal to 5. And if we have a greater chance that all the values above that threshold are above the above are equal to 5, or the target values at least are equal to 5, then that means that the values we predict as being 5 have a very high probability of actually being 5. If the values that we predict that we predict have a very high probability of being 5, then that means our precision becomes greater. Precision basically states, remember, that if a value is predicted as true, it is very likely to be true. If a value has a very high decision score, then it is very likely to be positive, or not positive, but or we could say true, right? True is the word we use for that. It's more likely to be true in that case. So if it's more true, then it's going to be more precise, because of the values that we predict as being true, it have a very high probability that those values are true, because it's very difficult for values with lower decision scores to go into that interval. So as we move the threshold to the right, we have a greater precision. Okay, we have greater precision. Now, when we increase the precision, let's talk about recall for a second. What is recall? Recall states that of all the true values, how many does the model classify as true? When we shift the threshold to the right, the number of values that are true values, that are actual true values, that no longer will reach the benchmark to be above this threshold, will decrease. Notice how when we shifted the threshold from the middle to the right, the 5 was removed. So now there are less values that are actually true that ended up going above the threshold that the model actually predicted as being true. So therefore, our recall goes down. So our recall went down and our precision went up, because our precision increased and our recall decreased. Okay? And so you can use the same logic the other way around. If you go to the left, what's going to end up happening? Well, that means more values are going to be shifted are going to come to the right of the threshold. They're going to have a decision score to the right of the threshold. If more values have a decision score to the right of the threshold, if it's easier for it to come above the threshold, then it's more likely for the values that are predicted as being true to actually be false. And if more values are predicted to be true than are actually true, that are actually false, then that means that the precision score goes down, but the recall score will go up, because of all the true values, more of the predicted values will fall above that threshold. So when we shift it to the left, you see that difference there. Okay. So that's the relationship that you have there. And so you see there that we have to make a sacrifice in terms of our threshold, that when we increase the threshold to the right, we make a trade off. When we decrease it to the left, we also make a trade off. And so that trade off must be considered. Now, in different situations, precision and recall can be sacrificed. So, for example, let's say you're working with, like, for example, a shoplifting type of service, right? Where you have a machine learning model that is monitoring different individuals, and based on their behavior that they're engaging in, we can determine whether or not they are more likely to commit a crime. And if they're more likely to commit a crime, then we will notify, let's say, some security guards. Okay. Well, in that case, what do we really want? We want the model to overanalyze individuals and overstate that, if even if an individual has a little bit of shady character, shady movements or things like that, that we would immediately report to the security guard that we should check this person, even if they have a little bit of weird movements or things like that. Well, in that case, we might have to, let's say, increase or decrease our precision, right? And we could still, in this case, precision, if the value is predicted as true, it is more likely to be true. So in that case, we don't really care if we have a very low precision, but if we have a high recall, that's what we really care about. Because of all the values that are predicted true, we want more of them to actually be true. So we might want a high recall compared to a precision. Okay, so you can see how in certain cases, having a lower precision and having a higher recall may actually be useful in that case. So that would be an example where even if you have a low precision, a higher recall would be expected. Now, in that case, keep in mind your harmony mean may be shifted downward, but that might not necessarily be a bad thing, because in that case, even though your harmony mean went down because of that lower value, it doesn't matter, because in your case, that would be less important to you. Okay, so that would be an example where you might want to consider the trade-offs. Everything is trade-offs, right? Everything in statistics is trade-offs. So that's an example of precision and trade-offs. Now let me go ahead and show you. There is a lot of analysis that you can do with this as far as working with our decision scores, because scikit-learn actually does allow you to access the decision scores that it uses in its internal when it's doing its actual modeling. But what we're going to go ahead and do is we're going to take a look at the outputs of some of the experimentation that other people have done, and then take a look at these outputs in order to kind of show how these trade-offs occur. So you see this graph here, and you can see here that as precision increases, and you can see how recall begins to decrease, right? So you can see here how those two are kind of inversely related, if you will, right? As one goes up, the other goes down. You can also see the different points at which each of these begins to decline extensively. So you can see here that recall and precision, so you have recall on the x-axis, precision on the y-axis. Once your recall goes below roughly zero point 0.4 or so, then, goes above zero point 0.4, then your precision really begins to drop extensively, right? And you really begin to see a drop once recall reaches 0.9. So like between like 0.9 and 1, you see a massive drop in precision. Okay, so if let's say to get rid of that other example that I gave you, let's say you wanted to create a model that was good at both precision and recall. Both of those characteristics were important. You couldn't make a trade-off. Well, in that case, you'd have to find some mean, some place where you don't give up more of one, yet you don't give too much of the other. Right? You have to find some equilibrium point, if you will. Right? And so in this case, you would have to try to find some equilibrium point on your particular graph. Okay, so that was with regards to precision and recall, with regards to the inverse relationship that you see in this graph, as well as the different points where we see that, hey, these begin to decline at much faster rates. All right, and so we added another equation to our error equations. So you see here that you have 2 divided by 1 over the precision plus 1 over recall. So that's another equation that you have there for the harmony mean. Now keep in mind, for the harmony mean, if even one of those two values, precision or recall, is smaller, then that's going to result in the harmony mean going down more towards a smaller value. Okay, so that was with regards to the trade-offs as well as harmony mean. And in the next tutorial, we will be going further on with the ROC curve and experimenting more with that and learning exactly how we can do that. From there, we'll go into multi-class classifiers and learn a little bit more about that. I'll see you in the next tutorial.